So should we get started slowly? Good morning, everyone. Also going to with me up. But quick announcement, there's a lot of food left from last night, as you know. So we're going to put it in the kitchen for lunchtime. If any of you want to get free lunch, you're welcome to help yourself. And today we'll start with Vardha Bennert, who's based in California State University. She's been visiting ESO for the last few months. And I guess you're going to tell us about the AGN galaxy scaling relations.
Celine. Good morning, everyone. And this talk is also with Mezcua, and where she's going to talk second. So if you look at the program, you will see that, so this talk is called AGN Galaxy Scaling Relations. There's another review talk called AGN Host Connections, and a third one called Black Hole Galaxy Collision at the Highest Redshift. These are just the review talks. So clearly there's a lot of interest in this topic. What we decided in this talk to focus on actually how do we actually measure both axes of these correlations. After a brief background presentation, I'll spend a bit of time on how do we actually measure black hole masses, what are the different methods and also the involved. Then I want to talk about specifically on the relation with stellar velocity dispersion and why that's important. And then I'll focus on reverberation mapped AGNs as a local baseline. And then Mar is going to talk about stellar masses and the black hole mass stellar mass relation, as well as the low end of the scaling relations, and then going all the way from the low to the high redshift universe. So that's kind of our outline for today's talk. So I don't think I have to motivate much in this audience here, but what are scaling relations? These are empirical relations that were discovered a quarter of a century ago at this point, so it makes me feel really old, I guess, between the mass of the supermassive black holes in the center of galaxies and the property of the host galaxy, for example, spheroid luminosity here, or stellar velocity dispersion. That is, as the name says, the dispersion of the velocity of the stars in the galaxy. Some stars come towards us, others are moving away from us. That Doppler broadening is the dispersion that we can measure in the absorption lines, and that's essentially a measure of the mass of the galaxy. And there has been, this plot here is for quiescent galaxies with different methods how the black hole mass was measured. And there's some debate if these relations exist for all morphologies or if it's mainly elliptical galaxies. If you look down here, there's thousands of references in a handful of review talks. So if I'm not citing you or your favorite reference, I apologize, but you can imagine it's difficult. And there will be lots of other talks in this conference also. So why do we care about these scaling relations? We heard that yesterday already by Sophie, where she was saying there's very different scales involved. So we have the microparsec scale of accretion for active galaxies onto the black hole, out to the parsec scale of gravitational sphere of influence of the black hole, and then out to the kiloparsec scale of the bulge. So very different scales. At the same time, the relations show quite a tightness, the M-sigma relation about 0.3 dex over a large range of masses. And so the way this has usually been interpreted is that somehow the formation and evolution of galaxies seem to be linked to that of black holes. And we'll hear a lot more about the inner region of the AGN in this review talk as well. So what I mentioned yesterday, what I'm a bit cynical about maybe is what I think we really have to be careful about. Just because we see a correlation, does that actually mean causation, especially if we plot it in double logarithmic scales? And so there are different reasons to maybe find evidence of a causation that's also needed for other observations. For example, AGN feedback, and with that I mean here negative AGN feedback, where the AGN through jets and winds and outflows not only regulates its own black hole growth through radiation pressure, for example, it can also quench the star formation by pushing out the gas or keeps the gas in clusters from cooling. And as we've seen yesterday already, this is really important and involved in all sorts of simulations, and it's necessary to match the cold dark matter simulations to the actually observed galaxy luminosity luminosity function where without it, we would overpredict the number of luminous galaxies. It seems to be important, at least in simulations, but observation evidence is still somewhat questionable, at least is there enough energetic involved? And there will be, I think, 3 different review talks coming up also that will talk about this in a lot more detail. Coming back to this question of causation, this is what this shows is if we start with an initially uncorrelated distribution between black hole mass and stellar mass, and all that has been done here is to merge these objects hierarchically through the natural averaging of the merging and the central limit theorem, you end up with this red relationship here. And so no need for any AGN feedback whatsoever. So how can we distinguish? Well, there are certain predictions that this makes. One is you would expect a larger scatter at higher redshift just because there haven't been that many mergers, as well as at lower masses for the same reason. And then also there's this whole debate on morphology, in particular pseudobulges, which are considered to be more disk-like and have evolved through secular evolution rather than classical bulges that are a consequence of mergers. So in this part, then pseudobulges would be preferentially outliers. Just as a background motivation, I'm going to talk a lot more about how do we actually measure black hole masses. This is a picture of a black hole. Okay, okay, that was, I don't know, maybe you're still asleep. My students are much better reaction, but of course, you know, that's not true. We actually have images of a black hole at this point, 2 black holes with the Event Horizon Telescope in M87 and Sagittarius A star. So M87 is 2,000 times further than Sagittarius A star, but also 1,000 times more massive. And so that's why these are the 2 objects for which we actually can do this. And there's actually a year later, there was a proof of the persistent black hole shadow, as this is called. What this shows is the photon capture radius, which is about 2.6 times the Schwarzschild radius. So that's how we can determine the black hole mass. Of course, through a comparison with models. It's a photon ring that is gravitationally lensed. So the combination of the event horizon and the light bending causes this dark shadow that is seen here. And there's ideas for a next generation EHT to include even more antennas. And so maybe in the future, we'll see a lot more of these measurements. But for now, it's only these 2 objects. And then a lot of black hole masses that I showed on my first slide have been determined through resolving the black hole gravitational sphere of influence, spatially by looking at gaseous and stellar kinematics. Of course, there's the Nobel Prize winning work by Andrea Ghez and Reinhard Genzel here, where they trace the stars in the center of our Milky Way galaxy in the near infrared, and some have completed a full orbit. And then it's the same how you measure the mass of the sun. If you know Keplerian base, if you know the orbit of the planets, the time it takes and the distance, you know the mass inside. You can also do this, for example, with gas, blue shifted, meaning coming towards us, Doppler shift, red shifted, moving away from us. That gives you the velocity. If you can resolve it spatially, I guess the colors don't come out well on the slides there. You can determine the size. Combination of size and velocity gives you the mass. And then the same for so-called mega-maser galaxies that are preferentially in type 2 AGNs that reside in this maser disk, water masers, for example. And then you can you trace it in the radio. And if you can spatially resolve this barometry, then you can also determine the velocity. Now, this is limited to the local universe, about 150 galaxies, since a lot of, we're hoping to find a lot of answers to the origin of these scaling relations by looking at higher redshift. So we need to use other methods to go to higher redshift. Now, one big step forward recently has been gravity, VLTI, so long baseline interferometry combining all 4 VLTs. And the technique used here is known as spectroastrometry. So This measures the flux-weighted spatial offset of each velocity bin. So we're splitting the line, for example, here Paschen alpha, we're splitting it up into individual velocity channels, for example, here blue shifted, and we're looking where is this being emitted spatially, and we see an offset. Why can we measure it to such great detail? Well, in interferometry, there's a phase difference that results in the fringe pattern, which can be measured much more accurately, much more precisely than the interferometric beam size. And this has been done so far for 7 nearby AGNs because they need to be very massive and they need to be bright and nearby to do this. But Gravity is currently getting upgraded to so-called Gravity Plus. And some things have already been completed, like they're upgrading the AO system and the laser guide stars. There will be laser guide stars on all 4 UTs, as well as including off-axis fringe tracking. And so what this means in practice, if you're an observer, you can go, your constraints, what you need for a fringe tracking star goes from currently 10 magnitudes within 2 arcsecond to 13 magnitudes within 30 arcseconds. So this really makes the sample that is accessible with this technique a lot larger. And so they're predicting that they can do hundreds of AGNs out to redshift of 2 or so. And then depending on what, it's always in the near infrared, of course, depending on what redshift, there will be different broad lines that are covered. What has been carried out for much longer than Gravity is so-called reverberation mapping, where you're kind of using a trick. So instead of resolving the black hole gravitational sphere of influence spatially, you resolve it in time. For that, you need type 1 AGNs, if they're varying, so you need AGNs that are varying, where the accretion disk flux varies as a function of time. So on the x-axis here is time. On the y-axis up here is the accretion disk flux as traced in the optical. What's nice about this part is we don't need to know why they're varying. We don't care about this. Some other people can study this. All we need is that they're varying. And since they're ionizing the broadline region, the gas clouds in the vicinity here, and they are re-emitting upon recombination, the flux of the broad lines, for example, H beta in the optical, will also vary as a function of time, but with the characteristic time delay, a time lag here, that depends on the size of the broadline region. We know the speed of light, so the light travel time, that gives us the size of the broadline region. And if you then combine, so the width of your broadline gives you the velocity. Again, combining size and velocity gives you the mass that must be enclosed. There's a proportionality here that actually is important because from this method alone, we don't necessarily know the geometry or kinematics of the broadline region. I'll get back to that in just a moment. I want to briefly compare reverberation mapping and Gravity. So reverberation mapping measures the linear broadline region size and weighted by variability. That means it is biased towards the inner regions versus Gravity that measures the angular broadline region size. That's actually already interesting because we can use that to get geometric distances to AGNs. And so this is still in the early phases, but if we get enough of these objects, eventually it could be used as an independent probe of H naught. So that's a whole different topic that I'm not going to go into today. But because it's flux weighted, it's more sensitive to the outer radii. And so far, when you compare these two sizes, there seems to be an offset in the sense that Gravity measures a larger broadline region size. One caveat here is that so far, Gravity measures in the near infrared, and the reverberation mapping is usually done in the optical on H beta, so on 2 different lines. So there's an intrinsic uncertainty. I'll talk about this a little bit more later. But the big advantage of Gravity is that it can go out to really high redshifts where the cosmological time delay of 1 plus z prohibits to do reverberation mapping. So you would expect a time delay of 1,200 days, the time lag of 1,200 days. And you have to cover it 10 times as long to get a realistic time lag. So this is just not feasible. But regardless, the reason why these two samples, the reverberation map sample and at this point also the gravity sample, are so important is because they are used as a secondary method known as the single epoch method. And I'm sure almost everyone has used this method in some ways or the other. So what this does is there is an interrelation between the luminosity in the continuum, 5,100 angstrom, and the size of the broadline region determined from reverberation mapping, or here from the red data points are from gravity. And we can understand this also from ionization principles, why this may be, why it might have this slope of about a square root. But then we can, so the reason why it's called single epoch is because all you need to do is take one spectrum of a broad line of your type 1 AGN, use the continuum luminosity as a proxy for broadline region size, combine it with your velocity, and again, you have your black hole mass. The same proportionality problem occurs, at least for reverberation mapped AGNs there. And so I think it's safe to say that the reverberation and gravity AGNs are the black hole mass calibrator beyond the local universe. They have been extrapolated to hundreds of thousands of AGNs to study evolution and what we know about black holes. So I think it's important to understand those well, right? Because that's all we can do right now. I want to talk a bit about this proportionality. So what's traditionally been done is that we're assuming the relation between black hole mass and stellar velocity dispersion for quiescent galaxies, these black data points here, also holds for reverberation mapped AGNs. So what we can then do is all we do is we're moving the red data points up and down on the y-axis, because we don't know their absolute black hole mass. We only know the proportionality. We move them up and down until they match. And that gives us this F factor, the virial coefficient. So it converts the size and velocity into a mass. And it depends on the geometry and kinematics. Of course, what this means is the F factor is only a sample average factor. It's not for individual objects that might not be the right factor to use. And I'll get back to this in a second. Which means that this is really the dominant uncertainty for black hole mass measurements is one of them is this matching, and it's 0.4 to 0.6 dex or so is your uncertainty on the single epoch method. There have been two ways forward, two improvements on reverberation mapping. One is so-called velocity resolved reverberation mapping. So what this shows, 4 different objects on the bottom here, different examples of how the broadline region looks like. So what this does, instead of looking at the time lag of the entire broad line, it looks at the time lag velocity resolved. So let's look at this object here. So on the x-axis is, this side is blue shifted, this side is red shifted, the red shifted wing of the line. So what you see, and up here is the time lag. So in this case, the blue shifted wing of the line has a longer time lag. What does that mean? The blue shifted wing of the line is the one that comes towards us, but it has a longer time lag, means it's further away from us. And the red shifted wing is going away from us, but has a shorter time lag, so it's closer to us. So this would be an example of infalling. And then you can make the same, argument with outflowing, and then there's something in between where it's just symmetric, which you might expect from Keplerian rotation. So there seems to be a variety of broadline region kinematics. So far, this has been done for about 90 AGNs. And it seems that disk-like rotation is dominant, which maybe that's good news because, maybe this supports that's actually virialized motion, so we can use our approach to measure a black hole mass. Inflow may indicate, that there is also still some accretion happening. Unfortunately, there has been no clear trend with any other AGN parameters, because that would be really nice if you said, oh, you only need to use this luminosity and then you know what your broadline region looks like. No, that we haven't found any other AGN parameter. The other step forward with reverberation mapping is so-called dynamical modeling. That's actually also used for gravity, for the gravity measurements. So what this does is it assumes different models of the broadline region. For example, a sphere, a disk. The disk can have different inclinations and different opening angles. And then it propagates. So you're observing some variability in the continuum. You're propagating this through your broadline region clouds and ask the question, how does my H beta flux look like? But not only the flux, but also how does the shape of the line looks like? Because we have both these informations, right? And then we can infer from that, what is the best model of my broadline region? What is the opening angle? What's the inclination angle? And more importantly, this method allows us to measure the black hole mass directly without assuming the Vera factor. And then we can, if we look at what do we typically see, there's a range of broadline regions. Most are thick disks seen at low to moderate inclination, which is probably expected since these are type 1 AGNs. It also tells us a little bit about the origin of the broadline region. Again, we have looked at so we can turn this around now. Since we have directly measured black hole masses, we can ask the question, what F factor would we get through our traditional method? So we have now, we can get individual F factors and look at what do the individual F factors depend on. The only trend we have seen is between the F factor and the inclination angle of our broadline region. And that's what you would expect. So if it's a thick disk, the more face on you see the disk, the less you will be able to see the rotation, because the rotation is happening in the plane of the sky. So you don't see the rotation, meaning that you underestimate the black hole mass. So you have to correct for that by using a larger F factor. So that means that the sample average F factor of 5, sure, it works as a sample average, but individual objects can be a factor of 30, So that's another uncertainty that is often totally ignored in single epoch mass measurements. So, it's, I think, maybe even 1 dex or so is more realistic here. Unfortunately, since we don't have a really good way to get the broadline region inclination directly, it doesn't really help us to calibrate much here. So I have one slide kind of talking about, what are the caveats. So reverberation mapping is mostly done on H beta, but there's a lot of other lines, Balmer lines, helium-2. So mostly H beta, but Balmer lines are helium-2, mostly for local Seyfert galaxies. The single epoch method has been used on all sorts of lines, from C4 over C3, magnesium-2, Balmer lines, Paschen lines, depending on the redshift and the instrument you're using. So that's, of course, a problem. There's some broad iron-2 underlying that's not always fitted because there's not enough signal to noise. We know that the broadline region is stratified, meaning that higher ionization emission lines respond more rapidly. So there can be a factor of up to 6 difference in time lag. That's also usually not taken into account. And then, we're extrapolating from local Seyfert galaxies to quasars across all redshifts. So, of course, there's uncertainties involved in, how does the broadline region depend on AGN luminosity or Eddington ratio? What about outflows? What about radiation pressure? So I think we can maybe discuss this later in our discussion. However, I think, yes, there are caveats, uncertainties, but at least the overmassive black holes by a factor of 100, we can't just argue away. So there's still something else going on there. I only have a few minutes left. I want to talk a little bit about the black hole mass stellar velocity dispersion. Why? Because, as I mentioned before, traditionally it's been used to determine this F factor. And it is also considered the tightest, meaning maybe the most fundamental. So it's important, but most studies especially also at high redshift, use just some aperture, either Sloan aperture or whatever. You integrate everything you get, and you're lucky to get any absorption line whatsoever. But there's very different sigmas that result depending on how strong is your AGN. What about the disk? Is the disk, which direction do you see the galaxy disk? So I think the best way forward is integral field spectroscopy for a robust measurement of sigma. And we did this recently. This is a PhD student of mine, Nico Winkel. He recently graduated and he's on the job market. He did excellent work on this paper. So we did this for the best reverberation map AGNs, meaning those that have directly measured black hole masses. We have HST images and IFU spectroscopy. And we can actually show for the first time directly that so far we assumed that the M-sigma relation holds. Here, because we have the black hole mass directly, we can show that they are the same between AGNs and quiescent galaxies, which maybe you're not surprised by, and we're not either, but still we need to prove these assumptions. And we also find that it's robust regardless of host galaxy morphology. I'm working on a follow-up paper on this where I'm looking at the HST images and the host galaxy decomposition, and we find the same trend that it also holds for spheroid luminosities regarding of host galaxy morphology. And so maybe AGNs are just a short phase in the evolution of galaxies where they're not offset from the relations at that point. Maybe that's what this tells us. Let me see. So one thing that we can now do, because the sample that we focused on, these reverberation mapped AGNs with directly measured black hole masses, we actually now have information on the broadline region inclination, and we can compare it to the host inclination. And what you see here is a scatter plot, which means that the broadline region is independent of host inclination. And that tells you something about the AGN feeding mechanisms. There has been another study recently that so far has only 8 objects where they use X-rays to get the accretion disk inclination, and they find a tight correlation between the accretion disk inclination from X-rays with that of the broadline region, which is as expected from our unified model, and it would support the disk wind model as the origin of the broadline region. Last slide here. So how can we move this to higher redshift? So I think I hopefully convinced you that M-sigma is important and maybe one of the most robust relations, but that's obviously impossible for high redshift. So what's been done at high redshift is to use ionized gas instead, in particular O3, with the idea that the gas motion is dominated by the gravitational potential of the galaxy. But of course, we know that there's outflows, right? The O3 line has blue wings. So how do we deal with this? Well, in one study, we suggested to fit it with a double Gaussian and then only use the narrow core to trace sigma, and that seemed to work quite well. But again, it seems to work well as a sample average, but individual objects can still be quite a bit off. So of course, there's uncertainties as well. And again, I think we can still not explain the overmassive by a factor of 100, and I think that's all for me. Thank you.
So we'll take some question directly related to the talk before we move to the second part. Any questions?
Hey, very nice talk. Learned a lot. So if I understood correctly, if you could measure the inclination somehow with something cheaper than reverberation mapping, you could reduce the scatter. I was wondering, what about radio jets and finding the angle of those?
Yeah, and I think one aspect might be this that I showed about the X-rays, and the X-ray people in the audience probably understand this a lot better than I do. That would actually be one way, using X-rays to get the broadline region inclination. And yes, a radio actually would also work. I think, in fact, there are 3 objects in this sample that are radio loud, for which the radio jet inclination has been measured, and it matches within 5 degrees to the Broadland region inclination. So that's really impressive because it's totally different models, and it actually also really supports this dynamical modeling, because there are people quite skeptical of that, you know, of course, as well. So yes, the caveat, so first of all, you need them to be radio loud, because if they're radio quiet AGNs, then how do you know it's not from star formation that your jet is from, right? And then I had speed dating with someone yesterday working on radio, and I think the problem with radio is also, we know from radio jets that they can be misaligned, like they vary over time, and maybe because the spin changes or something, like you have the outer radio jet looks like this, and the inner radio jet looks like this or something. So what if you only have resolution to measure the outer radio jet, and then you say, oh, it's not aligned with the disk, but there was, I don't know. And I think also, you know, what if the radio jet hits a dense medium and gets bent in the dense medium, but again, you don't know that, or you don't see it. So I think, yes, in principle, but of course there's also challenges, but maybe I forgot who it was that I talked to about the radio jets, if they want to chime in. And we can leave it for the discussion too.
Yeah, exactly. Yes, Vardha.
I have a question about the caveats of comparing what you get from gravity and from vibration mapping. So do you know if there are campaigns that are planning to use infrared lines?
Thank you.
Okay.
I am, yes. So I did, you know, there's only so much I present here, and I have some, you know, slides made up, but maybe I don't even need to show this. Yes, we are actually doing a campaign with an IRTF, a NASA IRTF telescope, as well as Gemini South, where we have band 1 observations of 2 of the gravity AGNs, and we're doing near-infrared reverberation mapping using the same line that gravity is using. And so if successful, this would be the first near-infrared reverberation mapping campaign, period, like using Passion Alpha and Bractic Gamma. So that alone is interesting, because then we can look at the stratification that I mentioned before. And then we would compare apples and apples. So we would reduce the uncertainty in the comparison between gravity and reverberation mapping. So yes, so that's a work in progress, and hopefully we can extend this right now.
So I had a quick question myself. So what about ALMA? I thought that some people
True. Yes. Yes. And I did not have time to talk about that
Okay,
as well.
okay.
Yeah. So that's true. There's also CO lines. Yeah. And I think I had another speed date with someone yesterday who talked about that.
and we
So-
see jets, you know.
Yeah, that's not my area of expertise, but I'd be happy to hear from.
Okay.
Thank you again.
Speaker then?
Yeah, because, sorry. Yes. Yeah.
Okay. So Vardha has shown you how we can measure black hole masses, also on the x-axis, the sigma, stellar velocity dispersion. I'll focus here more on the stellar mass, on the black hole mass stellar mass correlation, starting by how we measure the stellar mass itself. And one of the most widely used methods is the mass to light ratio. Probably you know all these Bell color correlations, right? We can have the mass to light ratio based on different colors. We have a bunch of them. This is all in the optical near infrared, but we can also use the UV luminosity to measure the stellar mass. However, the problem of using these mass to light ratios is that correlations are strongly dependent on the stellar properties, the properties of the stellar populations, like, for instance, the star formation history, or the D4000, for instance, or the metallicity of the stellar population. So another widely used method that most of you have applied for sure is SED fitting, spectral energy distribution. Here we have that multiple photometric data points, and actually the more we have, the better. are treated assuming different templates, and we have a wide range of templates here. We can have for the host galaxy, stellar templates for dust emission. Also, some of the codes here, like for instance, Seagull incorporates Asian templates and a Taurus template, but not all of them include this. So this is particularly relevant if you want to write stellar masses for galaxies that have an Asian template should be included in the SED fitting. And then something that should always be done, but it's not always possible, is to decompose the AGN and the host galaxy, right? Like even if you want to use SED fitting, you should first have the photometry from the galaxy alone without the AGN contribution. This has been possible up to Redshift 2 imaging a few years ago. You can see here how after removing the PSF, the central AGN, you see extended host galaxy emission. And with the JWST, we have been able to do that at redshifts higher than 6. Again, you can see here how after removing the point source, there's still extended host galaxy emission. So what should be done in practice? And what has been done in many cases is, first of all, AGN host galaxy decomposition. And after that, SED fitting to the AGN removed photometry. Okay, this is to derive stellar mass. And then if you have black hole masses from reverberation mapping or mostly from single epochs or only one, as Vardha was explaining, one spectrum with a broad emission line, like alpha or beta, you can plot your galaxies on the black hole mass stellar mass correlation. This is done in many papers, and overall you can see that there seems to be a correlation that extends all the way from massive galaxies and some low mass galaxies, but we'll go through the low mass regime later. And even in the massive regime, you already see that there are several data points that fall below the scaling relations. Why is that? One possibility is that these lower here galaxies, under massive, let's say, galaxies, have higher Eddington ratios, which implies they have higher black hole growth. So with time, because the black hole is growing, the points, the galaxies will move towards the relation, okay, with ascent vertically towards the relation. Yet, as I said, it's unclear what's going on for lower masses, for lower stellar masses, the low mass regime. Some years ago, we found that in the low mass regime, around 10 to the 6th, stellar mass is here in black hole mass, and this is sigma. This is for velocity dispersion below 100. There seemed to be a flattening. We were able to quantify in Martin Navarro and Mezcua. This was very exciting because this can have implications for understanding how the seed black holes form in the early universe. And let me go this into more detail. We've seen this sketch yesterday. I think Sophia showed it. This is an updated version, in which I'm adding the JWST AGN. So if you are interested in this updated version, let me know, because some people use this diagram for many of the talks, especially it's defense as well sometimes. Okay, so before JWST, we had many quasars at redshift 6 to 7 and with black hole masses of 10 to the 9, even some 10 to the 10 detected here. Okay? Now, with JWST, we are finding AGN of 10 to the 7 solar masses at redshifts up to 10. Okay? So this means that all these quasars and AGN here do not have time to grow from stellar mass black holes. We need to invoke more massive black holes, which we call intermediate mass, seed black holes, at redshift 20 or above. Okay? Now, these seed black holes can form via different mechanisms. One of them is the death of population 3 stars, the first generation of stars, which would yield seed black holes of between 100 and 1,000 solar masses. We can also have mergers of these seed black holes in nuclear clusters, again in the early universe. Or we can have direct collapse of pregalactic gas, and this would yield very massive seed black holes of around 10 to the 4 to 10 to the 5 solar masses. Now, in principle, all these seed intermediate mass black holes have time to grow via accretion and mergers and become the supermassive black holes that we detect at high redshifts here of 6, 7, 8, 9, 10. However, maybe not all these seed black holes grow and become supermassive black holes. Those that did not grow should be found today in dwarf galaxies as intermediate mass black holes with masses of between 100 and 10 to the 5 solar masses. So investigating the number of black holes, of intermediate mass black holes in local dwarf galaxies can tell us how these seed black holes form. And this is a very nice sketch from Greenstrader and Ho, in which you see that if seed black holes formed from population 3 stars, which is thought to have been a very common mechanism, then you expect a high black hole occupation fraction in today's dwarf galaxies. And also you expect the local scale relations to bend downward, or to have undermassive black holes with respect to the scaling relations for massive galaxies. While if seed black holes form via direct collapse, which is a peculiar mechanism, not so common probably, then you expect a low black hole occupation fraction in today's dwarf galaxies, and you expect a flattening in the black hole mass, stellar mass scaling relations. So the finding of a putative flattening here in the low mass M seems to imply that seed black holes form predominantly via direct collapse. Okay, but that's not the end of the story, because there are many biases here. In particular, we might be biased towards these more massive black holes, these direct collapse black holes, being easier to detect because they have masses of 10 to the 4 to 10 to the 5. So they are, of course, easier to detect than a 10 to the 3 seed black hole. Okay. And apart from that, more recent works found that in the low mass regime, there's no flattening, but just larger scatter. You can see here a few data points for dwarf galaxies, which there's no apparent flattening, and also the same here, right? In the low mass M, there's just a larger scatter. Okay, so it was a bit controversial, and indeed larger samples of AGN in dwarf galaxies are needed to populate this low mass N, because in the end we have very few sources here as to conclude anything. And we've been able already to do that with what we have from DESI. I don't know if you are all familiar with DESI. It's like the new SDSS, let's say, but 10 times larger, actually only in EDR alone, in the early data release, which is currently public. There are already more than 1 million galaxies. You see also that the resolution is way higher. It's between, I think, 2,000 and 5,000. For EDR alone, we have been able to do SED fitting already to derive stellar masses, finding as a result more than 200,000 dwarf galaxies when doing a stellar mass cut at 9.5 in logarithmic scale. So this is already a lot. But in addition to that, we have been looking for broad emission lines, particularly H alpha, and we've been able to derive black hole masses based on this. So compiling only EDR, all the galaxies for which you have stellar mass measurements and black hole mass measurements, single epoch black hole mass measurements, we are able to plot the black hole mass, stellar mass correlation. Here, each square is not one source. You can see here, these are number of sources. Okay, so that is misleading, but you can imagine how many sources we have in here. And particularly interesting is that here we have many sources in the low mass regime. So overall, what we see is that there's no flattening. There seems to be no larger scatter in the low mass N. So the black hole galaxy holds across mass scales. And this related to the implications that Vardha was talking about would mean that Asian feedback rather than mergers would be dominating black hole galaxy coevolution. This was all very local. Now let's move to high Z. Things get more complicated there. Before JWST, there were very few dwarf galaxies with AGN. Actually, with black hole mass measurements, there were only two type 1 AGN in dwarf galaxies. And type 2 AGN, we had way more than 1,000 sources, but of course without any black hole masses. So what we did before JWST to increase this is to use the Viper survey. I don't know if you know this survey. This is BMOS public galactic redshift survey performed with the VLT. There are more than 90,000 galaxies with a multi-wavelength coverage, so we can do STD fitting. And we did that for the broadline AGN included in the Viper survey, and selecting those galaxies that were dwarfs, so doing a cut in stellar mass after performing the STD fitting. So out of these 1,000 broadline AGN, we found 19 low mass galaxies based on either the finding of rotate beta, magnesium 2, or carbon 4. In the first paper, we went only up to redshift around 0.4. And then in a second paper, we found there were sources up to redshift almost 3. But this was a very exciting sample because nobody had found these AGN in dwarf galaxies at such high redshifts, again, before JWST. But what was more surprising is that when we measured the black hole masses, again, using single epoch, we found black holes of more than 10 to the 7 solar masses. In all the previous work on AGN in local dwarf galaxies, the black hole masses were of 10 to the 5 to 10 to the 6. It was very impressive for us to find black holes of more than 10 to the 7. And actually, of course, when putting these sources on the black hole mass stellar mass correlation, we found they were really offset. Okay, so these were the first overmassive black holes found in low mass galaxies. But then the same year, plenty of papers appeared on low mass galaxies hosting AGN at redshifts 5 to 10 with the JWST. In this case, the stellar masses came either from AGN host decomposition or acidic fitting, and the black hole masses again from broad Barber lines, especially H alpha. I think this was the first case, the first JWST AGN in a low mass galaxy at high redshift. But then you can see in this compilation by Maiolino, way more sources, all of them located again above the local black hole mass stellar mass correlation. Okay, so now we have overmassive black holes in low mass galaxies, but at redshift 5 to 10. Okay. So you might say, okay, that's not true. These are not overmassive black holes, and Vardha has already introduced here some possible selection effects. One of the first, let's say, caveats here is that maybe this is, again, a bias toward more black holes, brighter AGN being easier to detect because of the sensitivity limit of quasars and AGN surveys. However, and we saw this yesterday, I think by Sophia as well, that we have some black holes with very low accretion rates that are still overmassive from the local black hole mass scaling relations. Okay. Another possibility is that the scatter in the low mass N is very large, 1 dex, for instance, and that there are black hole mass selection effects. And then again, emphasizing on what Vardha said before, if black hole mass selection effects apply, then we would see this not only on the black hole mass stellar mass correlation, but also on the black hole mass sigma correlation, right? Because the problem would be on the y-axis. However, if we plot all these JWST AGN on the M sigma or the black hole mass dynamical mass correlation, we see that the sources are consistent. We're talking about redshift about 4 with these relations, okay? So the sources are not overmassive on the M sigma or black hole mass dynamical correlation. This is telling you that this is not a problem of the black hole mass itself. Otherwise, they would be overmassive also here. The fact that these sources are not overmassive, but they follow on the M sigma is again suggesting that the M sigma is the most universal and fundamental correlation. And this would imply that the formation of the early spherule must be linked to the early black hole. So let's believe, or let's assume that yes, we have all these overmassive black holes from redshift 0.4 to redshift 10. Now, what are the implications of this? The first one is that the black hole mass to stellar mass ratio evolves with time. And this is something that is supported by empirical models. We have, for instance, this line here from Pacucci, and also some Trinity models from Zhang, in which we see that the black hole mass to stellar mass ratio grows exponentially until the redshift at which we detect this overmassive black hole. And that after that, so the propagation to the local universe makes the black hole mass to stellar mass correlation flat, so that the sources would be overmassive also in the local universe. Another implication, or the contrary, an explanation for the black holes being overmassive from the local scale relations is the presence of AGN feedback. But we'll see a lot about this tomorrow and on Thursday as well, so I won't go into the details here. And then maybe for me, the most interesting implication is about the seed black holes. whether the finding that these black holes are overmassive can tell us something about how seed black holes formed in the early universe. And here there's again a discrepancy. So we find that some models favor light seeds. So light seeds are the ones with low, let's say, black hole masses of 100 to 10 to the 3. So those formed from population 3 stars. While other models favor heavy seeds, so those formed from direct collapse, having 10 to the 5 star masses. Okay. But in practice, the seeding signatures are erased. We are not able to distinguish between light or heavy seeds using these overmassive black holes, okay? At least not observationally. What we are able to do is to distinguish which is the black hole growth mechanism. And here on the left, we have all these overmassive black holes compiled from redshifts, as I said, 0.4 to 10. And they are plotted here as stars. And these red circles here, these are the simulations from Trink et al., assuming super Eddington accretion. And you see that the super Eddington accretion is able to explain overmassive black holes here, while the Eddington limited accretion model, which would be the gray circles here, does not. Okay. So in principle, these overmassive black holes, what they allow us to is to distinguish between growth by super Eddington or limited Eddington limited accretion. So supermassive black holes would require episodic, short and episodic growth phases of super Eddington accretion. Okay, so we've seen together with Vardha's part a lot of progress on measuring black hole masses through different techniques such as reverberation mapping, also gravity. Very important for AGN in particular as local calibrators. When combining high quality data with precise black hole mass measurements, we are able to verify the black hole mass scaling relations for reverberation mapped AGNs. And this applies very well at the local universe. When moving to high redshifts, there are many uncertainties here. If we just assume that all the local relations apply, so we have to be cautious both in terms of the y-axis, black hole masses, but also on the x-axis, so sigma or stellar mass. And despite all these caveats, we still think that the overmassive black holes we are finding seem to be real. And in this case, this can have important implications for the seed black hole formation models, not in terms of how the seeds formed, light versus heavy, but how they grow, either Eddington or Eddington. So thank you very much.
Any questions? Yes, Eduardo.
Hi, Mark. Very nice talk. You mentioned that maybe the most universal scaling relation is the M sigma. So in the local universe, sigma is the version of the bulge. How do we know that these high redshift galaxies have a bulge, or what is the sigma?
That's another uncertainty. Yeah, of course. We don't know. So far, the most we can do is decompose the galaxy into the PSF, so the AGN emission, and the host galaxy. But I haven't seen any papers in which they say like there's a bulge here. So the sigma, it's just the stellar velocity dispersion in the galaxy, not in the bulge. And this is another uncertainty, but also in the local universe, because sometimes we're using the sigma, as I said, from the galaxy itself. I mean, we're measuring the sigma for galaxies where there's no bulge. Okay, so it's not only a high redshift problem.
Also related to that, if I understand correctly, that it's not talking about this M sigma relation, but comparing this M sigma relation with the M star relation for those dwarf galaxies that you see high redshift is significantly off. It means those dwarf galaxies intrinsically different at high redshift towards low redshift, or is it simply because the measurement of the stellar mass is something different?
We were discussing this yesterday with Paula. Why are the AGN in dwarf galaxies overmassive in the high redshift, but not in the local universe? And the issue we were thinking of is that most of the searches that have been done in the local universe for AGN in dwarf galaxies, because they are interested in low mass black holes, they sometimes do a selection at 10 to the 6. So if you are looking for AGN in dwarf galaxies in the local universe and you find a 10 to the 7 black hole, you exclude it from the sample. And what you publish is only those that have black hole masses of 10 to the 6 or less. So we think this might have happened very often because many of the searches for Asian indoor galaxies focused on intermediate mass black holes, so low mass black holes. So I'm pretty sure that if we dig out the archive, I don't know, like SDSS, whatever, we will find many also supermassive black holes in the local galaxies. And this is a project I have in mind because, I mean, at least from simulations, we see that these supermassive black holes are expected to be found also down to the local universe. So they must be there. So far, maybe they have just been excluded. Examples. That's my.
So I see more hands, but Mara asked online her hands up. Mara, do you want to ask a question?
Yeah, thank you. First of all, both speakers, thanks a lot for your very interesting talks. Very, very, very nice. I have a question on the way in which the stellar masses are computed. We normally blindly take, I don't know, Bourgeois and Charlot stuff, and I was wondering whether these templates are actually good for fitting dwarf galaxies. Can it be that we were using completely different templates, the masses will be different, and then the selection will change dramatically?
Yeah, and actually, this is the focus of some works comparing different SED codes, but also different SED templates, and the stellar masses change, actually. So you must be very careful here as well, especially when including or not Asian templates. And again, most of these templates, as far as I know, are meant for local universe. So we are not even sure whether they should be applied for higher redshifts. So the uncertainties here are very high as well.
Thanks.
So, just a very quick comment that just to part of the discussion. I've seen many papers on the archive that present stellar masses, and then when they're published, stellar masses differ by a factor more than 10. So just to be careful.
How long is it? A comment and then a question. So the comment is that in a recent paper that was from my student Santiago Bernard, who is coming next week, we are already finding massive black holes in dwarf galaxies using variability
In the local universe.
in the local universe, redshift below 0.15. So I invite you to go to the paper. I also a question. So what is the implication of these overmassive black holes at high redshift in terms of galaxy evolution?
You mean towards the
Yeah.
local universe rather than this?
In general, like is this telling us that maybe this question of what is first, the chicken or the egg? We have
The
solved.
idea is that the black hole has grown faster than the host galaxy. Presumably, this has been possible at higher redshifts via super Eddington accretion. Simulations show that the overmassive black holes, well, that this fast growth, the black hole mass to stellar mass ratio should flatten towards the local universe, so that this faster growth of the black hole doesn't grow exponentially anymore. But still, actually, it would be very difficult to sustain super Eddington accretion across cosmic time, right? So even though you still expect to find these supermassive black holes in the local universe, the black hole growth should be diminishing and making it maybe more in peace with stellar mass. Otherwise, I don't think it's sustainable.
Tiago had a question. Some more hands.
Yeah, so I had a question about whether you know the link between the overmassiveness, let's say, with local environment. The reason I ask is that in one of the channels that has been discussed in the theoretical literature with lower redshift, I believe, is that if you have a lot of merging, because you have a massive object, you get idle stripping, within an overmassive black hole. Is there any way to observationally test that with very high redshifts?
Yeah, I mean, you can look for measures, also investigate like the environment, like whether field or denser or clusters. And for the vipers over massive black holes, we did that and we found no correlation. Even if you go to the local universe, investigating whether AGN in dwarf galaxies are more predominant in denser or less dense environments, there are no correlations so far.
Don't we see as many massive black holes in the world? All of them are just no longer because they don't have AGN signals. Of course, I mean, it doesn't work in the radio as well. It's not something that is secreting radio beams slowly or just episodically. From that, did you see?
Yeah, there are several papers on radio emission from Asian and dwarf galaxies. Spatially extended jets, there are like a handful, not really much. And about, I mean, this is a bias towards the active black hole being, of course, active, right? Of course, there might be way more black holes, I mean, massive black holes in dwarf galaxies, but we just don't detect them.
Reflection from the radio without assuming you have to have an optic radio in them.
Actually, we did that using Cosmos, the Cosmos VLA survey. Yes. And we found AGN in dwarf galaxies based on radio emission alone, no optical emission, up to redshift 2 point something. Yes.
That was the same as Jago. Thanks. So, a couple of years ago, I sort of did this exercise for the most massive black holes, the ones that are offset by how much they have to grow from like redshifts 2 to 3, redshift 0 to be on the local scaling relation. And it's like you need pretty high star formation rates or just mass accretion rates. Has anyone done this same exercise for the dwarf galaxies at the lower mass end? Assuming, let's say, the black holes don't grow anymore, right? So it's just the stellar mass that grows to catch on to the scaling relation. Has there been any sort of estimates of how much stellar mass growth do you need in terms of star formation or mergers or so forth?
Not that I can think of right now, but I'm pretty sure in some of these models or Bitcoin models and simulations, they have done this, especially on this group using semi-analytical simulations like Trinca, Valiante, and Snyder. I'm pretty sure if they haven't done this before, would be easy for them maybe to do it.
Okay, so what I propose now perhaps is that we move to the more general discussion. I think this is one more
just
person.
grab one chair. You can just grab a whole chair.
We should all sit, or it's up to you. I'm sorry.
We put together a slide with just some thoughts about discussion points, but of course, it's a totally open.
So I just wanted to propose that, I mean, even though we are here in front of you in this panel, the idea of this is that it's more of a discussion and not you asking them the questions that you want, because we don't have the answers for these questions. So a first topic that Vardha raised in her talk was, so we see this correlation, but we do not really know if there is a causation there. If there is a causation, this could be pushing for both sides, as we were talking also yesterday, in the sense of the AGN feedback regulating the star formation rate would affect mainly the sigma, but also the self-regulation of the AGN would affect mainly the black hole mass. Also, there could be this consequence of similar effects. So with this idea of the hierarchical growth and the mergers, maybe they could be kind of separately going through the same effects. So I wanted to know if you favor any of the scenarios, or if we're going to be just in between the lines saying, oh, it's a bit of everything. Yeah.
I just want to make a quick comment about the Yankee and Macho paper, which I actually think it's a very nice paper and encourage many people to read it. But there is one, I mean, this is often referred to as paper to demonstrate that through merger and central limit theorem, you get a correlation even starting from a non-correlated sample. But that experiment is done under the assumption that black holes and galaxies don't grow. I mean, you put mass into the black hole and the galaxy and you let them merge and you get a relation. In fact, we know very well that both black hole and galaxies between, say, redshift 6 and now, they grow in mass. The black hole, several folds, right? So that same paper shows that if you let the black hole and galaxy grow randomly, you don't get a correlation as you see. They need to grow more or less following the same time evolution. They need some synchronization method, which is much weaker than saying they have to grow in lockstep every time, but there must be the long-term, let's say the Madao plot, the long-term evolution of star formation rate and black hole growth, they need to be somehow synchronized. So I think that paper, in the way I read it, say that maybe the connection is not so tight, but there must be some synchronization mechanism, even if you then rely on merger to get a tighter correlation. I think that's an interesting lesson for me from that paper.
And also related to that, there have been many papers looking for a correlation between mergers and AGN in the sense of merger triggered AGN accretion. And there are, again, controversial results, right? But many papers favor this. We find that mergers trigger AGN activity, at least in massive galaxies. So somehow mergers must be involved in any way.
No, I mean, I would say we know that hierarchical growth of galaxy happens, right? You have mergers. So that must contribute to the forming of M sigma to some extent. So I guess I would, for correlation, I would say more like it is some combination of those. And the question is like, how much do each of them contribute to that rather than it has to be one or the other. And I guess that would point towards like using simulation to actually have clear predictions, like what are the changes you see if you implement feedback, rather than making this some kind of one versus the other situation, which seems a bit oversimplified. And also, I'll talk next week about mergers, which is a fun topic, and I think it's also not that easy, right? So we don't have a very clear answer to that if they really cause AGN, at least for the full population.
It might also be an issue of timescales involved, right? Like mergers have a very, very long timescale to evolve, and the AGN phase is maybe much shorter lived, and the gas has to go to the very center. So I think that's probably partially why it's so muddled, the field, because we have a hard time distinguishing this effect.
And other thing to just want to add is that for all the systems that are these are high redshift that are offset, majority of those are sort of bright, but also type 1 or unobscured AGN. Right, there's a missing population where it's very, very difficult to measure black hole masses that are very obscured. And in terms of feedback effects, we expect a lot of that to happen when things are very obscured. And so there's also this missing population of, we don't know where the most luminous and obscured systems find the, local scaling. That might also increase some of that scatter.
Places where everything goes, lots of star formation, lots of gas, lots of outflows, and also lots of AGN activity. Those are some of the benchmarks we have. Let's be locally what's going on. How can we split things up so we can measure things accurately? I have the impression, and again, not my opinion, separating. Those can hold some answers to measure things. Some of the oddities we're seeing.
I think AGN in Brooks is, I think, particularly difficult because of the exploration. So measuring black hole masses there, I think.
Can we use this, can we do some more work maybe on these sources to help us understand that shift and then to pull apart the different components and interpret what's happening?
I'm wondering what we can learn from the fact that you were showing that M sigma seems to hold, but not the stellar mass. So what does that tell us? Because I think that's interesting and maybe unexpected if you think that both. I mean, the question is what's really underlying, and my naive assumption would think that it's the relation with mass. It's the mass that's driving it. I mean, the galaxy mass, it's what it's related with, and so we're just using all sorts of things as proxy, sigma, stellar mass, luminosity, they all proxy for the mass, maybe even dark matter mass, like maybe that is the fundamental relation, which of course is much more challenging to measure. So I wonder what does it tell us if the M sigma holds in high redshift, but not the one with stellar mass?
I think this is related to what Eduardo was asking about the origin of the sigma. Right, so the fact that they are overmassive on the black hole mass stellar mass means that the black hole is growing faster than the galaxy. But the fact that they are not overmassive on the M sigma does it mean then that the black hole and the galaxy grow in tandem? Well, it depends on where the sigma is only from the center or from the whole galaxy. I bet that if we were showing the sigma from the whole galaxy in the same way as the stellar mass, then they should be overmassive as well, right? So if when a galaxy grows, the stellar mass grows, does the sigma also grow?
I think normally that people think is the sigma stellar mass relation is very stable, right? You have whatever the galaxy stellar mass is, the sigma should more or less in line with each other. So that is the question that I also want to know is that if there is a fundamental difference between the local one and the high redshift one. And is that you are suggesting is basically the sigma and star relation is different. That's what you are thinking of?
But in the local universe, in principle, the sigma, much as we can, comes from the bulge or from the center, while sometimes it doesn't. But while when we go to high redshift, the sigma is, I think, from the whole galaxy. But that's why I'm asking. So if there's a growth
differently, you say, it's because back to the same relation again, locally that you're measuring the sigma in the center, while you go to high redshift, you measure the whole galaxy, you're saying that the sigma is systematically biased to the higher velocity compared to the local ones.
What I mean is that if the high redshift sigma is that of the whole galaxy, then I don't understand why the black holes are not overmassive on the M sigma at high redshift.
I think this is pointing out the fact that there is a problem with the stellar masses, right? Or otherwise you would have to have sigma that increase outwards, which seems a bit strange.
Yeah, which is not.
Yeah.
And sorry.
Roberto, do you want to go
Yeah,
ahead?
sorry that I can't be here. I had my hands up, but I think it's relevant to what was discussed. That indeed, what as someone has hinted, probably the issue is the relation between sigma and stellar mass, or dynamical mass and stellar mass, because in the end, sigma is a sort of a tracer of the dynamical mass. And I think that the simulators in the room can confirm, but most simulations predict that in the low mass part of the galaxy, let's say below 10 to the 9, 10 to the 10, the dynamical to stellar mass is much higher than locally. So because of they are dark matter dominated and gas dominated, okay? So if the fundamental relation is the black hole dynamical mass relation, as was discussed, then automatically, regardless of the black hole physics, you do expect these black holes to be overmassive in the black hole stellar mass sigma, simply because these galaxies are undermassive in terms of stellar mass. Okay, so this is totally independent, regardless of what is the seeding and growth mechanism of black holes. It just comes from the fact that at low masses, these galaxies tend to be have high dynamical to stellar mass or high dark matter to stellar mass, and this, I mean, comes simply from I think most simulations. And on the stellar mass, I think there was a discussion about how reliable they are. Of course, they are totally unreliable and so on because it's difficult to measure them. But all works that try to refine them all go in the making the problem worse, in the sense that, for instance, the finding recently that in a number of these galaxies, the Balmer break is actually not stellar, but due to gas absorption, makes the stellar masses much smaller, okay? And so it makes the problem even more dramatic. And you can put the way you want, but in order to make the black hole to stellar mass compliant with the local relation, you would have to hide one or two orders of stellar mass, which is unseen with GWST. I think it's essentially, regardless of how you compute the stellar mass and so on, it's so hard to hide all of such a massive amount of stars that I think that simple uncertainties in the stellar mass are not capable of reconciling with the local black hole stellar mass relation. So I think there is a real effect there, and but it's not simply and it's not simply due to uncertainties. Yeah, so just my 2 cents.
Thank you.
My question is, when we're talking about these galaxies at high redshift and their sigma, stellar velocity dispersion, how do we know that these galaxies have stellar dynamics that can even be well approximated by a spherical genome? Are these spheroids or are they kind of disky or? Because with AOST, we're going to quite high redshifts.
Many of these AGN are in these little red dots.
Yes.
So compact and red. For the others, I really don't know about the morphologies, like if they are spinal galaxies or maybe, I don't know.
Because I mean,
knows better maybe.
measuring a single sigma, right?
And it's actually also gaseous sigma, so it's not, it's from gas.
Right, so
O3 line.
Wrong.
And yeah, and
missing something else.
like I was saying, there's outflows, but you know,
Not even outflows, just like gas, which is
true.
Well, I just quickly want to say, so maybe I'm wrong, but I think for a lot of the little red dots, they do careful PSF subtraction to actually try to see the host. Very, very few systems, they actually resolve something. So in terms of actual morphology, from my understanding, it's actually almost, possible to actually know what it is. But I could be wrong if somebody is more of an expert on measuring morphologies of little red dots. I thought it was very, very, very challenging to actually do that.
I guess that point also applies to dwarf galaxies, which can be in complex morphologies. Disky. How do you do with the sigma?
Yeah, just a slightly different point. There's probably somebody who knows a lot more about this than I do. If you're overmassive in terms of the black hole and you're trying to catch up by growing the stellar mass, how do you prevent that star formation feeding the black hole? Because just through stellar winds and so on, you would expect some portion of the gas mass to be thrown towards the black hole, and then the black hole would still grow. So yeah. So is it really possible to grow the galaxy's stellar mass without also growing the black hole at the same time?
like you can go much from the AGN or something to suddenly stop.
Well, if you have feedback, then the black hole is growing,
Yeah,
right? So that won't work.
You put gas into the black hole, you get the feedback. Stop formation. The galaxy has tons of growth. You're quenching the black hole.
But then you're not growing the stellar mass either. You are growing the black hole.
Yeah.
So once you're overmassive, can you ever not be? I mean, once overmassive, won't you be that way forever?
I think this is an issue for sure, and probably I think there is no way out. But I think purely on a speculative theoretical way, you could devise a way in which the coupling between the feedback energy or whatever the black hole is putting out, it could be radiation winds, happen on very small scales. If you can essentially affect, I mean, and this needs to be almost isotropic, because you need to prevent more material falling from essentially every direction. So you need to have an isotropic mechanism that couples the energy on the scale of the Bondi radius. If you can do that, then essentially you stop the growth, whatever, it doesn't matter whatever happens around the galaxy. But this is strange to think that this only happens for some black holes late time, because the rest of the population doesn't do that. Otherwise, we don't. We wouldn't have like this.
Something like that. I mean, if there is some self-regulation.
Yes.
You do need to invoke some magic.
Yeah, I mean, in some sense, when we were, there is one of the question of this workshop we were discussing with the coordinators is about on which scale does black hole self-regulate. You can translate this question and then you stop the growth of black hole and let the galaxy grow, or vice versa. This really depends on which scales the feedback is relevant. So if you have several alternatives, you can pick the one that you need. Yeah, I think this is a key question.
I mean, how could black hole ever grow? If such
This was the universal way that of course you would never. Yes.
So maybe
Who raised the hand before?
But it's just a quick comment, to be honest. I just wanted to also emphasize that I guess the AGN and low mass galaxies, high redshift, are likely not the progenitors of the AGN and dwarf galaxies and low redshift. So they're more likely progenitors actually of, they sit in very high over density. So actually, if you try to look for something like AGN Z11 and a large cosmological volume, any behavior like this, you're looking at the largest over density in the box. Likely rare high objects in relatively massive halos. So then there's actually a lot of potential for the stellar mass to catch up. It would grow a lot more massive and then come into agreement with the black hole, because like Roberto said, the densities are quite high at high redshift. It's ideal conditions for black hole growth. So you have higher halo concentration also at high redshift, a lot of gas. But then this will all naturally regulate shift. In terms of whether there are supermassive black holes and low redshift, yeah, it's an interesting thought, and also with the variability studies. But if they are there at low redshift, they won't necessarily be in the active phase, right? So it's another reason why we might want to see that we can only detect them dynamically, even they're overmassive. For a dwarf galaxy, they will still have a relatively so therefore it's more or less sphere of influence, so detecting them dynamically wouldn't be that much harder.
Maybe one thing, I don't really have a solution to this, but throwing another wrench to this discussion is the role of stellar feedback, which becomes usually more dominant in lower masses. So AGN feedback tends to self-regulate, becomes very dominant in the 12 solar mass or above. And then if you go below, the stellar feedback seems to actually play even more significant role. So that transition of stellar to the black hole self-regulation phase as a function of mass, maybe that is like another feature that we can't just think of self-regulation of black hole. Black holes doing everything on themselves, but rather you have to then, I think that the degeneracy with the stellar feedback and the self-regulation of black hole, that gets a little bit complicated, perhaps, that's probably explaining the stellar fraction is the ratio of stellar mass and halo mass is different as a function. It kind of peaks around Milky Way and it goes down below the Milky Way mass, and then it also goes down above the Milky Way mass because of the AGN feedback on the high mass end, and then the stellar mass on low mass end. Maybe that might be something that was related to what Roberto was referring to, and the low mass end, that the stellar feedback is also playing another role that complicates the self-regulation process, perhaps.
Yeah, although note that there are like more and more studies, both observationally and from the simulation side, in which they find that AGN feedback in dwarf galaxies can be as significant as stellar feedback. I think Sophie has one of those papers. So maybe because before we didn't have even AGN in dwarf galaxies, now we have AGN in dwarf galaxies and also AGN feedback, right? So I think so far we all assume that it was only stellar feedback dominating dwarf galaxies, but now that there's AGN, many with outflows, AGN feedback would also be playing a role, not only stellar feedback.
I would like to add a few comments on the discussion that we had. So maybe linking to the last is that, for example, in these sources at high redshift, this AGN, even if we do not consider the little red dots as a photometric selection, but the broadline AGN, selected from spectroscopy. When we look for outflows in the spectra, stellar or AGN-driven outflows, we do not identify this outflow signature, traditional outflow signature in oxygen 3 or other lines. And another comment that I wanted to add, and so this is still a key point that is missing regarding the discussion we had before. And also one other comment that I wanted to make is that the dynamical mass that were shown before by Roberto are computed using the velocity dispersion of the lines. And so considering the gas, translating then into star velocity dispersion using some correlations. And in particular, that plot was considering medium resolution spectra. When you go to higher resolution spectra, using always JWST, you see that the velocity dispersion of the line is really small, like at the limit of the resolution of JWST, so 20, 50 kilometers per second. And this moves what seems to be on the correlation between the supermassive black hole mass versus dynamical mass. What seems to be on the line, it is moved again towards an overmassive black hole, even compared to the dynamical mass, because if you consider the narrow line velocity dispersion as a tracer of the dynamical mass, you get this, because lines are almost unresolved. So this makes the picture even more challenging somehow. So both overmassive in terms of stars, if you even the stellar masses derived from the SED fitting, but also in terms of availability of gas that make this dynamical mass. And the third and last comment is that it's true that we cannot trust that at the level in which they are measured, maybe the stellar masses of these objects. But this is the method we used also for local samples. So it's the same approach we always use to measure stellar masses in local universe, medium redshift universe, or high redshift universe. So the fact that we obtain these results applying the same methods as we were using before is still, I think, even if we can say are not reliable, and we agree that they are not reliable 100%, but it's still, I think, super interesting and is still saying something about these objects, because systematically at this point, after years, we are seeing that the position of this object in that plot is more or less that one, compared to the scatter that we have overall at the other redshift.
To add to that final point, I'm still quite pessimistic about stellar masses. And I do think that there can be a redshift effect of the uncertainty, because at high redshift, you seem to have much burstier modes of star formation. Also, specifically in dwarf galaxies, you see that when comparing like UV to H alpha star formation rates, which operate on different timescales, for example. And then when you run your different stellar population synthesis codes with different star formation history models, even in non-AGN already, you can end up with uncertainties of an order of magnitude, specifically at high redshift, whereas at low redshift, the stellar mass is actually one of the more robust quantities you can infer in massive galaxies, at least.
But this should go both up and down, or are...
That's the thing that I'm still not understanding very well, because indeed, if the uncertainty is symmetric, then the fact that we continuously see these many cases of massive black holes would still tell us that there is something to it. But I don't yet have a good feeling for whether there can be a systematic uncertainty. And also when we take in then the the fact that we are not deriving the stellar masses of purely star-forming galaxies, but have to subtract the AGN contribution.
Silvia, how much time do you have for this? Should be finishing in a few minutes, perhaps. Yeah.
Right, so do you want to say any final remarks? And then if we want to keep on discussion also on the other topics that we listed, it's okay. About needing spatial resolution and how to do that for other surveys, we can continue that in the coffee break. So if you want to.
Yeah, I mean, that might be, I think Vincenzo is going to talk about, new instruments and all of this. There's a lot of new instruments on the horizon, I guess, as well, that will make things very exciting. And yeah, I think, the other questions we had about in reverberation mapping, we're ignoring radiation pressure in the models, and how does that which is probably okay at low redshifts, but if we're at a high redshift, luminous quasars, how does that affect our black hole mass measurements? And then Mar also talked a lot about black hole seeds, so now still a lot of open questions about what models are. So these are just more discussion points to think about. And we have a bit more time together, so.
Hopefully, radiation pressure and outflows and stuff. I think there's still a lot of uncertainty our assumptions and our densities and rely a lot on
True, that's also really important.
Well then, yeah.
Final question about reverberation mapping. You mentioned you have this Passion Alpha campaign. Curious to see how long you need to have some results. Is that a decade or? Sorry, and if it's a decade, is there something else we can do at higher redshifts? I've seen some papers that propose using a accretion disk reverberation mapping or like lens quasar where you have multiple images and you can do this faster.
So there's one study by Peter Williams et al. Where they did a lensed quasar at redshift of 2.8, I think, and where it's multiple lensed quasars, so they knew already they were studying the variability of the different images, and so they could predict when the next image is going to vary, and so they could time their campaign to that variability, which is of course really, really clever. And because they have multiple images, they get automatically like a timeline 4 times as much as if they only had one image. And if you understand the model quite well of the lensing, so you can use that. So they were successful, but it still took a few years, 4 years or so with Gemini. So you have to convince a TAC to give you that amount of time to make that worthwhile. But the ones that we're doing right now in the near infrared with the gravity ones are local ones. So how long a vibration mapping campaign takes depends on the mass of your black hole, which translates directly into the size of your broadline region. So of course, the larger the broadline region, and then you need some sampling, and you need like a factor of 10 or whatever, as long as your expected time lag, So the ones that we're doing right now, we should be able to do in a few months. So that's the good news. We were discussing the other day, what about reverberation mapping or intermediate mass black holes? Technically you can do those in the night, so that would be really nice. But there are other issues involved with galaxy contamination and all of that. Yeah, so how long your reverberation mapping campaign takes depends on your black hole mass and the redshift. So the more massive and the higher redshift, the longer the campaign.
Okay, so let's thank our speakers again and enjoy some.